All right, so at this point in organic chemistry, we've learned a number of different instrumental techniques. First off, we've learned mass spectrometry. For mass spectrometry, you should be able to determine the molecular weight of a compound. So using this technique, we're able to identify what our molecular ion peak is, as well as obtain some information about the number of carbons and elements in our sample. For example, with this particular data set here, we would pick out that 207 is a molecular ion. It's odd, which means it must contain an odd number of nitrogen. We can do our calculation, and we would determine that it likely contains 12 carbon atoms based on these numbers. From this, we were just learning how to incorporate this with IR spectroscopy. So if we're given an IR spectrum that goes along with this data set, we should be able to identify functional groups that are a part of this molecule. So we could look from left to right. Starting here, we would see two little fangs, which we could identify as NH peaks coming from the NH bond stretch. Looking at the CH region here, we should be able to distinguish that we have carbon-hydrogen stretches that correspond to sp2 hybridized systems and some that correspond to sp3 hybridized systems. Additionally, we would have a carbonyl peak and a carbon-carbon double bond peak corresponding with the CH sp2 hybridized stretches as well. There is a lot more detail that we could go into analyzing the fingerprint region, but that's beyond the scope of this course. But from this, we should ultimately be able to nail down combining these data sets together, knowing that we now have oxygen in our sample as well from the FTIR, that we would have a molecular formula of C12, H17, and O2. Now, from this particular molecular formula, there's a whole range of possibilities for structures here. Some of these are shown on the slide here. A lot of these involve very simple, minute changes in connectivity, but determining which one of these are just with these two instrumental techniques would be a bit of a challenge. What we're going to introduce to you now is a new form of spectroscopy, which is very powerful and allows us to really unambiguously assign the structure of a molecular sample. So this form of spectroscopy is called NMR Spectroscopy, and it stands for Nuclear Magnetic Resonance Spectroscopy, which is the most powerful technique an organic chemist has for structural determination. And combining it with mass spec and IR can really give us an unambiguous viewpoint of what a molecule is. Why it's so powerful is that we get an atom-by-atom view of the molecule, particularly looking at the protons and carbons that are in that structure. Because all organic structures by definition contain protons and carbons, it's a very powerful and useful technique for organic chemists. The main interaction that we're looking at here is an interaction of radio waves with the nucleus of an atom to change the nuclear spin state. Now, unlike IR spectroscopy, this is a very small energy change here. So we're typically dealing with very small energy interactions compared to the bond stretching interactions, which take a lot more energy to change in a molecule. Now, in order to observe this particular phenomenon here, we need to have certain conditions. So we need to have this very strong external magnetic field, which is often created by a superconducting magnet that is cooled with liquid helium and liquid nitrogen. While it says 4 Kelvin on the slide, to keep these things going, we often have to cool them down to this temperature, which, put in more common terms, is about minus 430 degrees Fahrenheit. That being said, while this technique has a high cost associated with the instrument, keeping it going, it really gives us the entire connectivity of a molecule from this interaction here and allows us to figure out the structure of it by interpretation of this data correctly. Now, there are a number of other elements that are NMR active. Essentially, an element can be NMR active if it has an odd mass and an odd atomic number, or both. It should have this property of nuclear spin. Shown on the slide here, all of the elements that are labeled on the periodic table have some form of NMR active nuclei. The most common one is proton, carbon, N15, F19 as well, and phosphorus 31. All of these are common elements that are in organic molecules, which is why this is such a strong technique for organic chemists. There are some elements that don't have any NMR signal. We'll talk a little bit about that later on. But in general, what we're hoping to get is the ideal situation is a spin 1/2 nucleus, for which these nuclei are all spin 1/2, gives the ideal behavior in NMR spectroscopy. So what's happening with this principle of nuclear spin? And so what's happening here is that we can think of nuclear spin as basically making each of the nuclei that are NMR active behaving like a bar magnet. So they have some sort of orientation that they prefer in an external magnetic field. And so when we place them inside a very strong magnetic field, some of them align with the magnetic field in a lower energy state, and then some of those that are against the magnetic field are placed in a higher energy state from that. Now, in general, there's a very small population difference between these two states because it's such a small energy difference. According to Boltzmann, that's what we get. And so we're really often looking at a very weak signal from NMR spectroscopy, which also adds kind of to the cost associated with it. But fundamentally what's happening here, we can just think of this as any other spectroscopy form where we have two states and we end up basically applying some form of radiation to it and then measuring the effect of what happens when that radiation comes back. And so we're basically manipulating spins going back from this alpha to beta state here, which allows us to perform this particular form of spectroscopy. So one of the things here is that all of our molecules are made up of elements that all have electrons in them. And these electrons behave in a peculiar way when they're exposed to this magnetic field as well. What happens is they begin circulating, and they actually begin circulating counter to the applied magnetic field. What this causes is that each nucleus then experiences a decrease in the applied external magnetic field to it based on the amount of electrons surrounding it. All right. So the more electrons that it has, the less this external magnetic field will be felt. Now, as we know from thinking about properties of electronegativity and bond polarity, we know that electrons are not uniformly distributed across a molecule. So for us, this form of shielding here of a nucleus is beneficial because it allows us to see differences within a molecule structure. So areas that have lower electron density from this ethanol molecule here, because it's connected to an oxygen, will have less electrons on the carbon, and so it will be less shielded because more of those electrons are pulled towards the more electronegative atom of oxygen. And we're going to see a higher excitation and change in the frequency of emission here. And if we contrast that with the CH3 group here, which is one removed from the oxygen here, it's going to have a higher electron density here, so it's going to have a greater shielding, and it's going to be then excited at a lower excitation emission frequency. So now we can see that the chemical environment, particularly the electron density at a given nucleus, impacts the frequency that we will observe in the NMR experiment. There's another thing that impacts that frequency, and that's the size of the magnet that's used during the NMR experiment. Because increasing the strength of a magnetic field will change the frequency that we have for emission for an individual nucleus. And so this is a problem if you want to compare NMR data acquired on different spectrometers, which can have different magnet strengths. So convention was adopted where we discuss these not in terms of raw frequency outputted from the spectrometer, but in terms of a scaled value unit scale that's called parts per million, or chemical shift, where we're correcting for the magnetic field that's used on each NMR spectrometer. So we'll often talk about the x-axis of an NMR spectrometer as a chemical shift scale, in which we're looking for parts per million, or ppm values. Now, in addition to this ppm scale, we had to determine and set a convention for what we were going to set as our 0 point. And from this, we picked this very electron-rich compound called tetramethylsilane, or TMS, which is often set at 0 parts per million, and it's usually our reference peak for our NMR spectrum. And so by convention, this is set to be 0 parts per million, and that's because the majority of organic compounds all come to the left on this x-axis here, and as they usually come downfield of most NMR signals from this. And so having this reference scale here and being able to scale for different spectrometers allows us to look at NMR data across many different instruments and compare them systematically. So one of the issues to point out here, particularly with C13, is, as we learned with mass spectrometry, C13 is not the most common isotope of carbon. Now, when we talk about proton, we have the opposite situation there, where proton is by far the most abundant isotope available for hydrogen. So almost any sample that we have with hydrogen atoms in it is mostly proton, or H1. Now, with carbon-based species, we only see 1% has C13. So C13 in our sample is relatively low for most of the things. That's only 1% of the carbon atoms in our sample that we run on NMR is responsive to the NMR experiment. The other 99% of the molecules that are there, are at carbon atoms, are C12 versions, and these are not responsive to the NMR experiment. And so proton compared to carbon NMR spectroscopy is a little bit easier because we have a stronger signal that we're working with inherently. In general, what this means in practicality is that C13 experiments tend to take a little bit longer to acquire. They require a little bit more setup. Now, the important things for you guys to think about as you're going to work through the tutorial that we're going to have in MNOVA, teaching you some of the properties involved with NMR spectroscopy and learning how to think about connecting structure with a spectra, is that, the hybridization state surrounding the C13 changes how the electrons are distributed. And because of that, there's a lot of patterns that we can bring in, putting into thinking about where these signals show up and how they're related to a C13 atom's environment. Additionally, you should be considering inductive effects, thinking about the electronegativity associated with an element and how that will push or pull electron density away from a carbon atom, as well as thinking a little bit about some resonance interactions that can happen in pi systems that can allow us to think about, again, how electron density is being pushed and pulled in a molecular structure. All right. So once you have a good handle on C13 spectroscopy, you can probably come back to this slide here, and if you're given a C13 molecule that we started with our first data set there for our C12H17NO2 molecular formula, you could probably narrow down from all of these possible structures I've shown on the slide here to at least one or two possibilities, just given the C13 data set shown right here.